The inspiration for this mathematical problem is based on a true event that occurred on a hike in the Alps with our dog Rumo at the center of the story. On our way, we came across an obstacle. Ahead of us stretched a wide enclosure with a great many horned cows in it, some of them on and some very close to our path, which cut right across the field. Naturally, we wished to avoid antagonizing the heavy cows with spiky horns and were worried about Rumo barking at them. At the time, he was only 2 years old. As we did not fancy walking around the field, we were left with finding the least dangerous route across. Leashing Rumo, we focused on crossing quickly through the herd and simultaneously tried to steer as far away from any cattle close to our chosen path. Thanks to luck and a bit of strategy, we safely arrived on the other side. Still somewhat exhilarated, my brother asked me, how would we try to solve this problem numerically? We then discussed solution for the better part of our hike. Back at home, I kept thinking about how one would numerically determine the shortest path, while also maximizing the distance to the cows, and I immediately fell in love with the idea, and I came up with solutions on how we could solve this issue. So, now I would like to show you 3 numerical approaches to solving this problem, beginning with what I call the regular grid method and from there progressing to 2 alternatives with increasing efficient runtime performance. Let's start by describing the problem mathematically. To do that, we start with approximate the field as a rectangle and mark the start and end point of the dog's path with a dot and star respectively. Within the rectangular field, the cows are distributed independently and randomly with respect to a uniform distribution. In our example, 10 cows, and represent their positions with these red crosses. The rectangle in this example is 30 meters wide and 20 meters high. For this example here, think about where would you go? Maybe up here or between here? But I don't think you would go between these 2 cows in the bottom. For the first approach, we represent the space within the rectangle as evenly spaced out points, which we call nodes, and these are connected by lines, also called edges. The nodes and edges form a square lattice grid, hence the name. To determine the shortest path from the circle to the star along the edges through the nodes, we can define a cost function, which defines the cost of how dangerous it is to stay in this location. The closer a node is located to a red cross, representing a cow, the higher the value assigned by the cost function should be. For my example, we could define the cost function like this, using R for the 2-dimensional position of Rumo and C of I for any cow in this 2-dimensional field we have here. Next, we can introduce the critical distance from the cow, which is called crit here in this cost function, and set it to 10 meters. Thus, if Rumo gets closer than 10 meters to any cow, we start getting into the danger zone, which means either Rumo starts barking or the cow starts moving to us. And in any case, we wanted to avoid this distance to any cow. And if necessary, and if we get closer, this will get more costly for us. The highest cost ranges from 1 for the node closest to the cow, which means basically we stand right to the cow, to 0.1 for the nodes beyond the critical distance. The cutoff value at 0.1 symbolizes that danger of being in the field as opposed to being completely safe from the cows behind. Our final cost function for this problem here is the maximum function through all the cows in the field, as the position of Rumo to any cow that is the closest to him specifies the cost at the given position. As you already noticed, I already colored the nodes accordingly from low to high cost with a gradient from blue to orange. Now that we have the cost of each node, the next step is to define a way to traverse these nodes. So let's zoom into a corner here. Here, the cost of each node are these. We can start traversing the node grid using the edges connecting the nodes. The way we connect the nodes allows us to traverse the field diagonally and walking along the rectangular borders of the field. In order to determine the shortest path with the minimal cost across the field, we use the shortest path algorithm provided by SciPy, which runs on edge weights. We can transform the node weights from earlier into edge weights by simply computing the average of the cost of the nodes connecting to a given edge. Once we have done this, we can use Dijkstra's algorithm to compute the shortest path from start to finish. Any last bets on how the path will look like? 1, 2, 3, here we go! Amazing, isn't it? You probably expected the path to go this way, and I also did so. Because it was so satisfying to watch, here's another example. Now, this regular grid method isn't the fastest in terms of runtime performance. Let me show you the computational complexity of this algorithm. Complexity describes how the computation time increases if we increase the number of cows, nodes or edges. The first step is the cost of computing the node weight. This is just number of cows multiplied by the number of nodes. The second one is the cost of computing the edge weights, with k being the number of edges per node. With this regular grid method, k actually equals to 4, which becomes evident when you see this animation here. To be more precise, it is actually a little bit less than 4 because we have boundaries conditions and nodes on the boundaries, the lower one and the left one, actually don't have any nodes. Final cost is the cost of computing the shortest path. In this case we use the SkyPy version shortest path with the Dijkstra algorithm, and the documentation guarantees a complexity of the number of edges plus number of nodes, and these all multiplied by the number of nodes. If you solve this formula by also adding the constants and following the rule of the big O notation, the whole algorithm complexity will end up being n squared. We have to think of another strategy of placing nodes in the field, as this current one scales by the number of cows, hence the n squared. In our case also, the ratio of 1 to 100 for the number of cows to the number of nodes provided a good resolution without losing accuracy. This means we have to create a new strategy of placing nodes more cleverly, as well as reducing the number of nodes without losing accuracy. Can you think of a way? There is a method that perfectly fits the type of this problem. It is the Voronoi diagram. A Voronoi diagram divides a space into regions based on the distance to a set of given points, where each region contains all locations closer to one specific point than to any other. It's a bit like drawing boundaries so that everything inside each area is nearest to its own center point. The Voronoi diagram basically creates our desired path around the cows with the furthest distance away of them, which is exactly what we need. Let me draw you the Voronoi diagram on the same problem field as before. Do you see how the edges perfectly create the path for us to follow? Using the Voronoi approach, we first have to compute the cost of each node, like previously. But in the Voronoi diagram, this is not as straightforward as it was before. See, we are missing some nodes across the boundary of our domain. The Voronoi edges shown in orange are the ones which do not have the connection to our boundary, which is absolutely necessary for our case, as we also want to walk along the boundary. There are two ways to solve this. The first approach would be to find the specific outgoing edges, here shown in orange, and compute their intersection points with the boundary. This is quite tedious. We will instead focus on the second option. The trick is, we mirror the whole field on each edge of the rectangle. This way you are creating Voronoi nodes across the intersections. Let me visualize this on the top of the boundary of this rectangle here. As you can see, this allows us to compute the missing nodes and edges across the boundary on top. Doing the same step for the other boundaries, the left side and the bottom one, as well as on the corner edges, as we also need the corners of the rectangle, this would look something like this. As we now have all of our desired edges and nodes, it is time to compute the cost of the edges. With the Voronoi diagram, we cannot average the node weight as we did for the regular grid, because here the edges differ in length, which is something we have to consider when computing their costs. Let me show you why. Each edge is of different length, but they are both equally distant away of their respective cow. The left edge has a much longer time of traversing, hence it has to be much more costly than the right one. To reflect this issue, we can discretize the path into steps and compute the cost of each subnode. Note that these subnodes are regularly spaced between them, which allows us to use a numerical integral method. In our case, we use the Simpsons method, giving us the result of this edge. We can do that for the remaining ones as well. Now that we have finally everything what we need to use Dijkstra again to compute the shortest path, any guesses where it should go this time? Okay, watch out, here we go. Okay, this is a little bit unsurprising. It's the same one as before, but it is also showing us that mathematically this approach is similar as the regular grid method, which is a good sign. Let's use Voronoi on the larger one like previously to see if it also uses the same path. As you can see, we end up with identical paths again. Some minor differences as the Voronoi approach cannot cut corners. However, compared to the regular grid method, Voronoi is here in this example about 100 times faster than the other one. Let's see by looking at the computational complexity of Voronoi and how much it is different. This time, the first step is to compute the Voronoi diagram. This is of cost of number of cows multiplied by the logarithmic of the number of edges. The second step is computing the edge weights, which is just number of edges. And the final one is again computing the shortest path using Dijkstra. Solving this time, this whole equation will give us n log n, which is a much better improvement than the previous approach. Even better, we have fewer nodes to compute than on the previous one. But hold on a minute, I think we could do better. Normally my plan would be ending this video with more simulations of these, but I was talking with one of my colleagues in the office about this project of mine, and when he was thinking about this whole thing, he came up with an alternative optimization approach. Instead of finding a path from start to finish that minimizes the total sum of each weight, he suggested we focus on minimizing the maximum edge weight along the path. Let me show you an example of why this difference could be interesting. There are two possible ways here that we could pass this field. Either going close through these two cows, or choose the longer path with further away of them. The Dijkstra algorithm would choose the path for which the sum of the edge weights is smaller. But our new approach, on the other hand, would identify the longer path as the best one, because it maximizes the distance to the cows at any point of the path. So how would we implement such a method? It is time now to introduce you a new type of algorithm, which is called union find. The union find algorithm, also known as the disjoint set union, is a powerful data structure used to manage a collection of disjoint sets. It supports two fundamental operations: the find, which identifies the set an element belongs to, and the union, which merges two distinct sets together. We already have a strong connected graph, in which every node can be reached through another one. Nothing in our case is disjoint. But hold on for a minute and let me explain why this algorithm is suitable for us. Using union find, we can construct a subgraph from our original graph by progressively connecting the least costly edges, defined here as those with the greatest distance to their respective cows. We do this until we find the path from the start to finish. To do so, we provide union find with a sorted list of all our edges from the least to the most expensive. Let's see how union find finds the desired path of our beloved example. The first connected edge we unionize is this one here. It is the one with the longest distance from its respective cows and the first one on the sorted list. We continue with this process until we find a connection from the start to finish. The final edge, shown in red, is the most dangerous one to traverse. As union find only builds the subgraph, The next step for us is to use an algorithm that finds us a path from start to finish. In our case, we use the depth-first search algorithm, also in short DFS. Visualizing the DFS algorithm looks like this. You can see how it visits node step by step until it finds the ending. Out of pure chance, the path it found is identical to the one gotten from the regular grid or Voronoi algorithm. But when we use again this more complex example, the path union find finds differs. This doesn't come as a surprise, considering that our union find approach is mathematically different than the other two methods. Now, you might be wondering how union find compares to the regular grid and Voronoi approach in terms of computational complexity. Same as the previous method, we had to compute the Voronoi diagram and the edge weights. Before running the union find algorithm, we had to compile a list of edges from the least expensive to the most one. We do this by sorting the list in this case, using for example quicksort. And quicksort has a complexity of number of edges log of number of edges. So you can already see, union find has a complexity of n times alpha of n. And you might be wondering, what the hell is alpha of n? I'm glad you asked. The alpha in our complexity analysis refers to the inverse Ackermann function, a wildly fast-growing recursive function, but in reverse. The mathematical formula of the Ackermann function is this one. Solving this function recursively will give you these numbers, for example. The last number is not even computable, it is too big. And the inverse of the Ackermann function is defined as this. As n is for us the number of nodes, we can safely say it is around 3, but it will never go over 4. But why does the union find algorithm even involve something as the inverse Ackermann function? The reason lies in the way union find checks whether two elements belong to the same subset of nodes. Each time it performs the find operation, it traverses the underlying tree structure, which is constantly rebalancing itself. Thanks to its self-adjustment, future searches become significantly faster. Lastly, the depth-first search algorithm is of complexity number of nodes plus number of edges. If we would solve this whole function, we will end up with, drumroll please, n log n. So the same as the previous one. Even so, runtime wise, the union find approach is a tiny bit faster than the Voronoi approach. I benchmarked all three methods. With the first regular grid method, I set the density of number of nodes to cows to being 100 to 1. Keep in mind though, we got to this improvement by solving a different mathematical problem than in the first two approaches. Either way, the union find is the faster one. Let's compare the pros and cons of all three algorithms. The regular grid method has its advantage of making the heat map visible, for example, but the other two Voronoi approaches are outperforming in performance-wise against the regular grid method, no doubt. A con about the union find as well, it does not care at all about the length of the path. Some of you might ask, who could use such an algorithm? I was thinking about maybe GeoWizard could use it when he does his new straight line mission and he has to cross a field of sheeps. Thank you all for watching my video. Special thanks goes to these people here I listed here, and also for everybody else who have contributed in any way to my video. And If you're interested in my code, it is open source on GitHub. I provided a link down in the description. And in the end, I would also like to thank Rumo. You wanna say anything, Rumo? Busi. Busi. Okay, he doesn't want to say anything. But yeah, wanna go? Let's go, Rumo. Go.